Okay, so in this video, we are now starting with the idea of kinetic energy. So we've talked a lot about gravitational potential energy. Now let's move on to kinetic energy. So just as how gravitational potential energy was energy due to the position of an object in a gravitational field, we say this is the energy of an object due to its movement or speed. Now you probably also know the expression for this, but in AS what's also important is that you know where the expression comes from. So you also need to know the expression in which as to the derivation for this, so how we get the formula for this. So let's say that initially this object is moving with some speed, some initial speed u, and eventually it speeds up to some final speed v because of a force F acting here, right? So some force was applied, this object gains some kinetic energy, so we are supposed to know. In fact, even let's leave out F for now, and we know that this guy has some mass m, so we need to find an expression for the change in kinetic energy. So that's literally what the question is. So find an expression for the change in kinetic energy all right, let's start with this. So again, we know that this is some energy, but we also know that energy is basically just another name for work. So if we can find the expression for the work done, then all I have to do is to set this equal to the kinetic energy expression. So the way that this object must have sped up is some force F was applied, and you can also see here that this guy covered some displacement S in the direction of the force. So I can say that the work done is F into S. All right. Additionally, I can say that force, because force is not something which was given to me, that's in purple, so I just wrote that. I can write this in terms of mass times acceleration times S. But again, the problem is acceleration and displacement are not variables defined by the examiner. So I need to get rid of this and somehow get in u and v. So do you know of an equation that links u, v, a and s? U, v, a, s, u, v, a, s. That is the third equation of motion. The third equation of motion, which was v square equals u square plus 2as, because you need to get rid of both a and s, you can make that the subject. So that becomes v square minus u square over 2. So here I'll write m into v square minus u square over 2, which I can then also write as half, okay, let me write this here, half m v square minus u square. And the formula that we have been used to seeing in O levels was basically half mv square, which you get if you say that, all right, if this object starts from rest, so u is 0, and that is the formula. Kinetic energy is half mv square, right? So this is the formula that we need to know how to use. And additionally, in AS level, we also need to know how to derive this. So we basically took the help of three equations. One was work done equals force into displacement. The other one was F equals to ma. And the third one was the third equation of motion, v square equals u square plus 2as. This is something that the examiner does ask in MCQs. So till this point here, this was really the change in kinetic energy from some initial and final speed, and this is also a useful expression. However, some people do mess this up because this is half mv square minus u square. Some people, what they do is they think of this as half m v minus u squared, which is wrong. It's not subtraction and then the square, it's first the square, then the subtraction. So this is something that needs to be kept in mind. Also, pretty much like any other energy, kinetic energy is also a scalar. So this v here is speed, not velocity, right? So we don't care about direction as with any other form of energy. Now let me actually take this here because I'll talk about something with respect to this. Now, the other ideas, and you also don't find a lot of MCQs for us to practice with just kinetic energy, the amount that we've studied yet. But there's something else that I do need to talk about. So first of all, if we talk about this with respect to proportions, right? So if I say this is for constant speed, how is the proportions set up? So half is a constant, v square is also a constant. So in that case, kinetic energy is just proportional to m, just like how gravitational potential energy was also proportional to m. But what's special is this case for constant mass. Now if mass is a constant, so half is a constant, m is a constant, so all of this together is also a constant. And what I get here is that kinetic energy is proportional to the square of the speed. Now what this means is that in direct proportion, what we said was that if mass doubles, kinetic energy doubles. If mass triples, kinetic energy triples. If mass halves, kinetic energy halves. But in this is, by the way, what is called direct square proportion. And what happens in direct square proportion is basically any change that happens in V is squared and then passed on to Ek. So for the sake of argument, let's say if speed tripled, then kinetic energy would increase by a factor of 3 square, which is 9. So this is something that we need to be very careful with while using the formula, and needless to say, the examiner does pose questions like this. So let's do a short sort of exercise to understand this idea. So this is a sort of table that we'll have to fill in. So kinetic energy is Ek when the mass is m and the speed is v. So through a set of different exercises, I'll see how proportion works in the case of the kinetic energy formula. So if mass doubles, what would happen to the kinetic energy? Well, by direct proportion, it's simply just going to double. So this is going to become twice of Ek. Right? Similarly, if mass becomes 1/3 of what it is, and again in both of these cases there's no change in the speed, so it's still v. So I can say that because it becomes 1/3 of whatever it is, so Ek is basically the same, which is 0.33 Ek. Now if we talk about speed, so if speed triples, what would happen to the kinetic energy is that the kinetic energy would increase by a factor of 3 square, so it would become 9 Ek. So 9 times whatever it was. By the way, this is like this. Similarly, the case after this, let's see if I can shift this writing slightly. Okay, I can't. So anyway, now if speed becomes half of what it is, so that means kinetic energy would become half squared, which is 1/4. So this becomes 0.25 Ek, like this. This is here. And now, what if both of these change? So what if mass halves, speed doubles? Now, if you did not know what I just told you, then you would be very tempted to say that because mass halves, speed doubles, they should be cancelling each other out. But will that really happen now? Let's see. So because of the mass halving, kinetic energy also halves. And because of the speed doubling, this would now become 2 squared times whatever it is. One of these 2's cancel, one is still left. So the kinetic energy overall doubles. And the reason for this is that speed has a greater impact on the kinetic energy than the mass, right? So mass just causes it to halve, whereas speed causes it to quadruple, right? Last case then, So ek, mass becomes 3 times what it is, speed becomes 1/4 times what it is, so it would become 1/4 square, which is 3 over 16, which I think is 0.1875, or to 2SF I can write that as 0.19 ek, right? So these are just some ideas that we saw. Let's also talk about those type of questions which are rate of kinetic energy. So rate of kinetic energy. So rate of kinetic energy means delta ek over delta t. Now how are questions like this asked is that kinetic energy, again just half mv square divided by t. So sometimes the examiner gives you, again in this case as well, a mass rate question. So it would say that every second 5 kg of let's say water is accelerated from such speed to such and such speed. So find the rate of increase of kinetic energy. In that case, it's basically given you m over t, which is m dot. So I can write that as half m dot v square, right? But also because the kinetic energy questions are linked with efficiency, conservation of energy, so we cannot do a lot of past papers right now. So past papers we'll put on hold. First we'll go through the concepts and then come back to past papers which link kinetic, potential energy, ideas regarding friction, efficiency in the later videos. So don't worry, we'll meet again in the future videos.